So, hello everyone. Today we will be presenting our project on brain tumor classification using convolutional neural networks, a deep learning approach to support early and accurate diagnosis from MRI scans. So, what is the motivation and problem statement? So, brain tumors are a critical health concern. Diagnosing them early is essential, but often relies on radiologists, which can be subjective and time consuming. We aim to build an automated system using deep learning to assist medical professionals with faster and more accurate diagnosis. About a dataset. So we use the Kaggle brain tumor MRI dataset with over 7,000 labeled images. It's split into training and testing sets with a roughly balanced distribution across four classes: glioma, mini glioma, pituitary tumor, and no tumor. So this is about our dataset. It is around the training set has around 5712 images and the testing set has around 1311 images. So now coming to the exploratory data analysis and class imbalance. So our exploratory data analysis showed that the no tumor class is slightly overrepresented, which could lead to bias. So we carefully examined image formats, pixel distributions. So if you see here, we have carefully examined the image formats, pixel distributions, and planned for augmentation to handle this. So this is about our data preprocessing. We have converted images to grayscale, resized images to 224 into 224 pixels for consistency, and normalized pixel values by scaling them to 0 to 255 to 0 to 1. We have also split our dataset into train and test, where train consists of 70% of the dataset. The augmentation techniques that we used are rotation, height with shift, shear transformation, zooming, which we did 0%, flipping, and brightness adjustment. So it was necessary for a more balanced and generalizable dataset, ensuring that better model performance when classifying unseen MRI scans. Augmented image visualizations. So we have generated multiple variations per image, increased dataset size to improve model generalization, and handled class imbalance with augmentation. About a model. So our CNN model includes convolutional layers for spatial feature extraction, followed by pooling, batch normalization, dropout for regularization, and finally, dense layers with softmax for classification. So if you see in our neural network, the convolutional layers have ReLU activation, batch normalization to speed up training and stabilize activations, and pooling layers to reduce dimensionality and computational complexity. Dropout layers are there to prevent overfitting, and fully connected layers for final classification. We also have a softmax output layer for multi-class classification. About our training and optimization. So we have trained our model using Adam Optimizer, which is used for efficient optimization. It combines the advantages of momentum and RMS prop optimizers. And the learning rate is 0.001, which controls the step size during training. The loss function. Categorical cross entropy is used, which is suitable for multi-class classification. It measures the dissimilarity between predicted and actual class probabilities and helps the model learn correct class probabilities. Early stopping is used to stop training if validation loss doesn't improve for 8 consecutive epochs. It prevents overfitting by stopping before the model memorizes noise. Reduce LRO on plateau. So we have a factor of 0.3 and patience of 5 epochs because it is used to reduce learning rate when validation loss stops improving. So this was about our model. So based on the model that we used and the training and optimization that we used, we were able to achieve a very good accuracy. So the train accuracy is, we see there is a gradual improvement reaching to almost 100%, which indicates strong learning. The train loss consistently decreases, showing effective conversions. So the loss is decreasing and the accuracy is improving. The model fits training data well. And next step for us is to validate the generalization of a model. Now coming to our performance metrics. So all class show strong prediction performance. So if we see in this glioma, meningioma, everything is around 1, 0.91 and 0.92. So our confusion metrics shows a very good prediction performance. The glioma and neotumor, nearly perfect classification, 98 to 100% correct. And meningioma, slight confusion with glioma and neotumor, but up to 4% is the problem. And overall, the model demonstrates excellent class-wise precision and minimal misclassification. Performance matrices. It shows if you see in the graph, it shows consistent performance. All classes show high precision, recall, and F1 scores. So it is not biased to a particular class or to a particular type of tumor. And if you see for no tumor and pituitary, perfect or near perfect scores across all matrices, which is precision, recall, and F1 score. In mini glioma, there is a slight dip in recall, but impacting F1 score slightly. But overall, it is also a good performance. The model maintains balanced and robust performance across different categories. Next is the class distribution. So we see no tumor has the highest sample count, which is around 410. Other classes like glioma, meningioma, pituitary are fairly balanced, which is around 300 each. And slight class imbalance exists, but this is because if you see in real world scenario as well, all these different types of tumor comes in cancer category, and no tumor comes in no cancer category. So overall, if we consider tumor or no tumor, it's a very good classification. So, but overall distribution support fair model training without heavy skew. When it comes to prior work, each team member has experience with traditional machine learning models like linear regression, classification, random classifiers, but we have not previously worked with convolutional neural networks and definitely not with image data sets. So it was a very new opportunity for us to develop expertise in deep learning based image classification. And we have experience with exploratory data analysis, but not on this project. References. So we have referred this data set from Kaggle from South Nick Barbar, and we have also went through some references online like the brain tumor overview and brain tumor fact sheet in order to understand which are the most important factors that we need to consider in order to train our model.